All right, we are going to do 4.2, which is logarithmic functions. This is your introduction to logs, taking them from exponential to logarithmic. I'm just kind of getting into it. 4.3, we'll get into even more of the rules and stuff. So, first of all, we did exponential. So, exponential, you could have like b to the y equals x. And this would be considered being in exponential form. So if you ever have to put anything into exponential form, it's going to need to look like this. Now, if you can wrap your head around the fact that a log is just an exponent rewritten in a different way, it'll help you kind of remember the rules and stuff. And someone once showed me a quick little trick how to change this into exponential. Start at your base and circle around your equals. This will be the base of your log. So it'll be log base b of x, and then it equals y. So log base b of x equals y. This is in logarithmic form, or log form. And you can do the same thing going backwards. Just start at your base and circle around the equals. So start at your b, so it's b to the y equals x. And that's just a kind of an easier way of helping you remember how to get from one to the other. All right, so checkpoint 1, that's actually exactly what we are doing. In checkpoint 1, we are going to write as an exponential form. So we're going to convert log to exponential. All right, so we have 3 problems to do for checkpoint 1. We have 3 equals log base 7 of x. We have 2 equals log base b of 25. And we have log base 4 of 26 equals y. All right, so we're going to convert each of those into exponential. They're in log. So like I said, you're going to start at your base. Our base here is 7. Go 7 to the third equals x. And we're just converting it right now. Later we will be solving, but right now we're just converting. So you stop. That's all you have to do. All right, next one. 2 equals log base b of 5. So our base is b. We circle around the equals. So it'd be b to the 2. And then back around the equals equals 25. And then the last one, it doesn't matter that it's written like backwards with the log on the left. You still start at your base and circle around. So 4 to the y equals 26. All right, so that's converting log to exponential. Now checkpoint 2, you're going to go the other way. Checkpoint 2, we're going to convert exponential to log. All right, so problem A. We have 2 to the 5th equals x. For problem B, we have b to the 3rd equals 27. And for C, we have e to the y equals 33. All right. So we're going to do that very similarly. We are going to start at our base. You can kind of see my cat down there. we're going to start at our base, which is 2. So it's log base 2 of x. And then it equals your exponent, because a log equals an exponent. And that's it. We're just converting right now. This next one, our base is b. So it'd be log base b of 27 equals 3. And then this last one's actually kind of unique. It starts the same. We have log base e of 33. And then it equals y. Okay, which that's okay. But if you'll notice, like on your calculator, e is always associated with the ln button, which is actually natural log. I think it comes from log natural in other languages. That's why it's backwards for us, but I don't think it's backwards for other people. Log base e is a special kind of log. It's actually the natural log. You write that and you just know that the base is e. So the natural log of 33 equals y is actually the proper way of writing that one. You don't usually write log base e. Okay, so log base e of x is the same thing as the natural log of x. Just saying that base e is natural log, is something that's just assumed. Or you know, just kind of how it works. Okay, so the next thing we're going to do, put that up there for another second. The next thing we're going to do is we're going to evaluate some logs. Alright, so checkpoint 3. Okay, so the first problem we have is log base 10 of 100. Now, the first thing that's kind of unique about this one is the base 10. And base 10 is actually, it's just your regular log button on your calculator. So the other button here, this log is base 10. You don't usually write in a 10, like it would just be log of 100. But this one, I want you to get to the point where you just go straight to the answer, where you don't have to set it up. But if you need to look at what it looks like, you can put maybe an x out there and take it out of log form. So 10 to the x equals 100. So that would mean that x would have to be 2. So log base 10 of 100 is 2. The hardest thing about doing these is you have to switch your thinking. The most common wrong answer is 10 because people think 10 times 10 is 100. But really you need to think, how many times do I multiply 10 to get to 100? And that's 2 times. All right, problem B, we have log base 5 of 1 over 125. So this one's a little tricky because it's flipped upside down. We can set it equal to x, so 5 to the x equals 1 over 125. So I know this one is flipped. So that actually would be a negative. It would have to be a negative exponent that would flip it. And then 5 to what power is 125? The one way you could do this is just kind of use your calculator and count. So like 5 times 5, that's 2 5s, not enough. Times 5, there we go, it's 125. It took me 3 5s to get to 125. So x would have to be negative 3, or the answer is just negative 3. Because 5 to the negative third is 1 over 125. All right, C, we have log base 36 of 6. Maybe you can kind of figure out what this equals. It's kind of different because we're getting smaller instead of getting a bigger number. I mean, I guess 1 over 125 is smaller, but I mean, 5 to 125 gets bigger. So 36 to the x equals 6. All right, so I'm going to approach this one a little bit differently. I'm going to make like bases. So 36 is 6 to the 2. So we have 6 to the 2x equals, and this would be 6 to the 1. And then what you would do is drop your like bases. So 2x would equal 1 divided by 2x is 1/2. And remember something to the 1/2 power, like if we look back up here, 36 to the 1/2. 1/2 power is the same thing as square rooting. So it'd be like taking the square root of 36, and the square root of 36 is 6. So that's why 1/2 is the answer, and it does actually make sense. All right, problem D. We have log base 3 of the 7th root of 3. So if I set this equal to x, we'd have 3 to the x equals the 7th root of 3. Okay, so remember the 7th root of 3? That's like having 3 to the 1/7. So that would mean that x would equal 1/7. And that would be your answer. So the root is a fraction power. Okay. All right, checkpoint 4 and checkpoint 5 are still evaluating. If you look in the textbook, you do have a textbook inside MyMathLab. You get a digital textbook. That's one of the other reasons, because you guys don't have access to your textbooks, because I know most of you left it in your classroom. And if we go back, I'm going to have to look around the classroom and figure out where y'all left them. That's okay. All right, checkpoint 4. All right, so same thing, we're going to evaluate. There are rules that go with this. I'm just going to have us think about it for a second, and then we can kind of generalize it and make a rule out of these two. All right, so first one, you have log base 9 of 9. So what we've got going on here is our base matches our number. So if we need to do the whole setup for this, we can, or I do want you to start thinking, okay, 9 to what power is 9? Which that would be 1. But if you need to see it written out, when we get into 4.3, you're not going to be able to do this writing it out thing anymore. But for now, these notes I will. So 9 to the x equals 9, which means 9 to the x equals 9 to the 1, so x equals 1. So if these two match, the answer is 1, always, because a number to the first power is always itself. All right, for B, we have log base 8 of 1. So this one's a little bit tricky because it goes to 1. So 8 to some power equals 1. So the only thing that x could be, the only power it could be raised to would be 0. So it's 8 to the 0 power equals 1. And that's kind of the rule there. If that's a 1, the answer is automatically 0. All right, checkpoint 5 we're going to evaluate. Okay, for A, we have log base 7 of 7 to the 8th. This one's just, it's kind of a crazy one. Both of these two, the A and B in checkmate 5, I say just kind of look for the odd man out, and that's going to be your answer. So if we set this equal to x, you have 7 to the x equals 7 to the 8th. So you drop your bases, x would have to be 8. And that's your answer. And it's the odd man out. Because 7 to what power is 7 to the 8th? It would have to be to the 8th power. B, you have 3 to the log base 3 of 17. And this one's crazy, but your odd man out is 17. This one actually is not a log problem. This one is actually an exponential problem. If you set this equal to x, you would take it out of exponential form, have log base 3 of x equals your exponent, which is log base 3 of 17. So log base 3 of something equaling log base 3 of 17, the x would have to be 17. Okay, so that's our answer there. So yeah, it's just kind of the odd man out. Okay, so that is evaluating logs. Next thing we're going to do is we're going to graph logs. And we're going to use our graphs of exponentials to kind of teach us how to graph logs. So checkpoint 6. So we're going to graph a log as an inverse of an exponential. Okay, so we're going to graph f of x equals 3 to the x. And g of x equals log base 3 of x. So we're going to compare these two graphs. I know we graphed 3 to the x a bunch of times in section 4.1. Oops, let me draw my axes in there. Alright, so first of all, f of x equals 3 to the x. If we did a table for x, you're putting in -2, -1, 0, 1, and 2. And evaluating the y values at those points. So to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9. These would be the flip. 3 to the -2 is 1/9, 3 to the -1 is 1/3. And we'll plot those just the same way we had the other day. Now remember what an inverse is. An inverse is when you flip the x's and the y's. So let's see what happens when we go to graph g of x equals log base 3 of x. First thing I'm going to do is I'm going to make it y equals log base 3 of x. And I can't make a table out of values of that. So instead, I'm going to take it out of log form. I'm going to make it 3 to the y equals x, which looks just like this, except instead of putting our numbers in for x, we're going to put our numbers in for y. Putting the -2, -1, 0, 1, and 2 in for y. So 3 to the -2 is 1/9, -1 is 1/3, 0 is 1, 1 is 3, and 2 is 9. Okay, so plotting those points. We have 1/9, -2, 1/3, -1, 1, 0, 3, 1, and then 9, 2 is way out there. Alright, so this is g of x. That's our log function. That first one was f of x. And remember what an inverse is. It's flip over the line x equals y. So if I drew in x equals y right down the middle, you'd see they flipped over each other. And the other thing that happens is the asymptotes flip. So the first one, f of x, had an asymptote at y equals 0. So the log graph actually has an asymptote at x equals 0. And that's the graph of the two functions, showing that it's an inverse of each other. Now, all that flipping and stuff that we did with the exponential, you can do it with this as well. We can do the horizontal shifts, the flips, and then the vertical shifts. Okay, so translations of log functions. This will be the same chart one more time. Now it's in for logs. Okay, so our parent is f of x equals log base b of x. Okay, that's what we're starting with. Oops, I'm kind of running out of space there. Okay, so first will be our horizontal shift. And again, this is something happening inside the function. So, and it's opposite, just like before as well. So g of x could equal log base b of x plus c. Or g of x could equal log base b of x minus c. Okay, so that first one, remember they're opposite, so plus would take it to the left. So this shifts f of x left c units. This one shifts f of x right c units. Okay, that's a horizontal shift. Then you have your reflections. This is your negatives with my stupid mnemonic. I's and y's, x's and o's. You could have g of x equals negative log base b of x. Or g of x equals log base b of negative x. Okay, so this negative is on the outside. So we have x's and o's. On the inside, y's and i's. Okay, so this will flip f of x over the x-axis. This one will flip f of x over the y-axis. All right, and then the last one is a vertical shift. Okay, this is a plus or a minus on the outside of the function. So we have g of x equals log base b of x, and then the plus c on the outside or g of x equals log base b of x with the minus c on the outside. So the plus will move it up. And the minus will move it down. Okay. Fine, there's 2 in the book. Usually do. 59 and 61. Oh wait, just kidding. 54 and 56. I left my pre-written notes at school, so I'm pretty much doing everything from memory. Thought to grab my textbook, just not. Like, I have a folder of all my notes. I just forgot to grab that. And we are not allowed back in, so it is what it is. Alright, so let me do number 54 and 56. Okay, so we're going to first of all graph f of x equals log base 2 of x. And we're going to use that to graph number 54, which is g of x equals log base 2 of x plus 1 with the parenthesis. And then number 56, which is h of x equals 1 plus log base 2 of x. So the 1 is on the outside of the function. So we're going to graph, I'm just going to go ahead and do all 3 of these on the same set of axes. It also says to talk about the asymptote and then the function's domain and range also. So we'll do all that fun stuff. Alright, so first of all, our parent, which is f of x equals log base 2 of x. So we haven't done this one yet. So I'm going to change it to y equals log base 2 of x. And then convert it. So 2 to the y equals x, taking it out of log form and putting it into exponential. Make a table of values. Put in for y, -2, -1, 0, 1, and 2. Alright, and then 2 to the -2, we'll flip it and make it 1/4. 2 to the -1 just flips it and makes it 1/2. Anything to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So graphing these points, we have 1/4, -2. We have a half, -1. 1, 0, 2, 1, and 4, 2. Okay, so this one has an asymptote at x equals 0. And this is f of x. Alright, and then the domain is from this way over. So the domain will go from 0 to infinity, not including 0, so 0 would get a parenthesis. And the range would go from forever down to forever up. So -infinity to positive infinity. Okay, so that's what we have for that. That's the original, that's our f of x. Now we're going to just translate this to get our others. This next one we have, for g of x, we have plus 1 inside the parentheses. So it's going to move to the left 1. Because remember, it's opposite. So I'm going to move all these points left 1. And what's going to end up happening with this one is the asymptote will move also. So now our asymptote is at x equals -1. So this is the graph of g of x. Has an asymptote at x equals -1. Running out of room. The domain would just shift a little, go from -1 to infinity. And the range would still be negative to positive infinity. Both with everything with parentheses. Okay, that's g of x. Alright, and then finally, h of x. We're going to add 1. We're going to add 1 to our original function, the original f of x. So it's all going to go up 1. So our green graph, every point goes up 1. So it will keep the same asymptote as the original. Yeah, they're kind of all getting squished there. So this is the graph of h of x. It has an asymptote same as the original at x equals 0. So its domain will also be the same as the original, 0 to infinity. And the range will go forever down to forever up. And that's how we do those. So I hope that was helpful. Next thing, okay, let's talk about the domain without the graph. So we're going to go to checkpoint 10, I believe. Oh, no. Okay, checkpoint 7. So we're going to find the domain without a graph. Alright, and we're given f of x equals log base 4 of x minus 5. And this does go like with the asymptotes of the graphs and stuff like that, but we're not going to graph this one. We're just going to do it algebraically. So if we're taking the log of x minus 5, all you do is take your x minus 5 and make it greater than 0. Just like our domain up there, it went from whatever the asymptote was to infinity, not including the asymptote. That's why there's no equal to here. So you move the 5 over, you have x is greater than 5. And this also has a shift to the right, 5, because you have minus. So it makes sense. So the domain then will go from 5 to infinity, because that's x being greater than 5. It's not bad to do it algebraically, actually. Okay, we're not doing 8, we're not doing 9. I'm not going to do 10, it's the same as that. I feel like there's one more thing I wanted to cover. I don't want to stop this video. I think there is, yes, okay. I talked about it, but I didn't write it down. And that's common logs. Dang, paper bleeds through. Okay. So we talked about base E in the beginning. We did not officially talk about base 10. Common logs have a base of 10. Okay, so if anything is written without a base, it's understood that the base is 10. So like number 82 in the book, this goes back to what we were talking about before actually. You have the log of 1000. And it says evaluate. Now the nice thing is, you do have access to a calculator. You just do log of 1000. You get the answer of 3. I could do that in my calculator because the base is 10. There is a way to change base. We'll talk about that later. But what you're doing is your base is 10. It's equal to something. So it's 10 to the x equals 1000. Since there's 3 zeros, x would be 3. Okay, so base 10 is understood. So like 84, kind of one of those special ones, but if you have log of 10 to the 8th, this is one of those where your base and your number inside your log match. So you have a base 10. So 10 to what power is 10 to the 8th? Your answer would just be 8. And actually, well, the same thing would happen with E. Okay, so like if you're doing number 88 and it had the natural log of E, that's your two numbers matching also. So your base is E. So E to what power is E? It'd be to the first power. So just like log base 10 of 10 would be 1 also. Number 91, you have the natural log of 1 over e to the 6th. It's flipped. If you wanted to unflip it, you just throw in a negative in the power. So you could make it the natural log of e to the negative 6, which means it's e to what power is e to the 6th. It would be negative 6. Okay, so just some quick practice to get into. Like I said, again, we'll do it some more in 4.3. I hope this helps with 4.2, and you should be able to do your 4.2 homework inside of my math lab. Good luck. I hope everything's going okay with your digital learning, and I hope you are staying safe.